Hey class, this lesson is on forces with pulleys and forces with angles, and we are continuing with the Unit 1A overview for Objective 3, where we're solving problems involving forces, and we're just using and applying the same concepts we've learned before into different situations. This situation, specifically, I'm referring to is going to be, the first one is the Atwood machine. This is an Atwood machine. An Atwood machine is a system that has two masses on either side of a pulley system. So the pulley's purpose is just to transfer the force from one mass to the other mass. So that shows by if the left side's motion is downward and it's pulling downwards, well, the right side's mass is not going downwards, it's going upwards. So we're going to have to look at like the specific qualities of this system to be able to analyze it quantitatively. Oh, don't want to zoom in on that. Keep that playing. So the first quality of an Atwood machine is that since there is a string on both sides or cable and it goes over the pulley, that means there must be a tension force, and that this tension force T is going to be equal then to this tension force T as well. So like T1 is equal to T2. That's the first one we'll note. The second one we'll note is that the left side mass is going down and the right side mass is going up, but they should be going technically in the same direction because one's pulling the other. So in order to do that, we need to identify a new system of positives and negatives. And because the pulley is rotating the force, then we actually have to kind of rotate our positive and negative axis. So instead of rotating it, I like drawing it up on the top and just recognizing on the top of the pulley where there's positive and where there's negative. I often choose the heavier mass to have the positive side and the smaller mass to have the negative side, and that's just because I know that the heavier mass is going to pull the smaller mass, so I want the acceleration to be positive. So I'm going to say this is positive and this is negative. Now, in order to do that, that means that on the left side, we have down is negative and up is positive, but on the right side, we have down is positive and up is negative. So we know this like rotates like the force, and therefore rotates positive and negatives. There's one more thing we want to identify, and that's that since this object is connected to a string, and since this string we're just going to assume is taut, there's no stretching in the string, then both masses are moving at the same acceleration. And so the left one is moving down, at least in the picture, the left one is moving down and the right one's moving up. So technically, like we said from the second point, they're moving in the same direction. So, but we do know that A1 is equal to A2. So that the acceleration from the first mass is equal to the acceleration from the second mass. So in both of those cases, then we're just going to say we're going to use just T, and we're just going to use A in all cases, where there's no friction in the pulley. So let's look forward towards the individual free body diagrams of each mass. And our goal is to look at the individual forces and then combine them and analyze the system as a whole, and then come to a conclusion with that. So if we're only looking at the first force, well, we said that what down is negative and up is positive from before. So let's write that down. Down is negative, up is positive. Or we can, see this like this and go like that, and that gets to the same purpose. So I know in mass 1, I know that mass 1 is going to be smaller than mass 2, so therefore it's probably going to be accelerating upward. So I know that there's this tension force exists, and that must mean that there's a weight, which I'm going to use W1 just for ease. I could use FG1, I'm just going to use W1 for weight of mass 1. And I drew the vector smaller than tension because I know that the tension is going to pull mass 1 up. So I have, what's my net force of 1? And that's equal to, well, I start with my positive variable, which is T, and I go T minus W1, and that's M1A is equal to T minus W1. Cool. Let's go to the next one. We have also the same tension force T, but I do know that this mass 2 is going to have a larger force of gravity downward because it should be accelerating downward. Also, to identify the positives and negatives, we said that down is positive and up is negative, or that, up here we can go, this is positive and this is negative. And I can determine my net force for mass 2 is equal to, start with the positive variable, W2 minus T. So that gives me M2A is equal to W2 minus T. And when I look at these two equations, right here and right here, I notice that there's an A and there's a T that's in both of them. So I know I can at least substitute. So I'm going to choose substitution. I'm going to solve for, I want to solve for tension because I want to leave acceleration in my last equation, because in the end I don't want to solve for tension force. That's like, doesn't matter to me. They're equal on both sides. It cancels out. I want to find the acceleration that's occurring in this system. So I'm going to solve for tension. I get T is equal to M1A plus W, and this one I get T is equal to M2A. Now I get W2 minus M2A. Now I know that tension is equal to each other, so I know that this equation, M1A plus W1, is going to be equal to W2 minus M2A. So I'm going to take both of those, and I'm going to set them equal to each other. And now we're looking at the system as a whole. Now I have M1A plus the force of gravity of 1 is equal to the force of gravity of 2 minus M2A. I want to continue, and I want to solve for my acceleration, so I need to move my M1A and M2A on one side and my force of gravities on the other, my weights on the other. So I get M1A plus M2A is equal to W2 minus W1. I'm going to factor out my A on my left side, so I get A times M1 plus M2. And then I want to divide by M1 plus M2. And I get acceleration is equal to, because this cancels out, is equal to W2 minus W1 over mass 1 plus mass 2. Now, this is our final equation for the Atwood machine, but this shouldn't come to you as a shock, because let's look at the top, the numerator, W2 minus W1. Well, when we look back to what's actually affecting the acceleration of this Atwood machine, well, it's dependent on the forces due to gravities from both W2 and W1. So the top is really just the net force, because the T's cancel, but the W2 and W1, that's what's battling. And the bottom is just M1 plus M2, so that's just the net mass. So in the end, in all Atwood machine problems, we have an acceleration is equal to the net force divided by the net mass. And you'll see it here, but really it's just a substitution of net force divided by net mass. You might ask me, why did we go through all this process if we just got to net force divided by net mass? And the purpose is that physics problems sometimes aren't as easy as just applying some simple net force divided by net mass. This type of work will show up at some point in time. So getting that practice of really looking inside of the system and breaking it down. And the one good skill to have is taking something simple and then looking at the individual parts and using the individual parts to get to that simple equation. And then it's like this beautiful connection between a system that looked complicated but actually is very simple in the end. So we're going to use this net force divided by net mass in other situations. in which, of course, you could go down this complex route, but in the end, I strongly suggest just thinking of it as net force divided by net mass, but recognizing what are the forces at play. So this next situation is with the heavy trolley. So in this heavy trolley, and let's move this stuff up so we have some space. Oh. Below. We have a heavy trolley on a table. It's accelerating forward. There's a pulley and the weight's going down. And then we want to use the net force divided by net mass, but first we need to identify the net forces. So let's draw our free body diagrams for the heavy trolley. And in this case, we're going to assume that there is friction on the table. So here's my heavy trolley. Go ahead. I'm going to pause this. You draw the free body diagrams for both the heavy trolley and the weight, and we'll meet in a few seconds. All right, so for my trolley, there's a tension force, and the tension force is greater than the frictional force because it should be moving to the right. There's a weight and a normal force, which are equal, and they cancel each other out, so the trolley is not moving up or down. So only it's definitely moving to the right. The weight has a downward force that's greater than the tension force, but the tension forces are equal. So when we look at the net force, we have to kind of get rid of this normal and weight because they cancel each other out, and also they're not traveling, they're not in the same direction as the motion. So we look at what force is acting to push the cart forward and what force is acting to oppose the cart. In this case, we have a net force, which is, well, the force is acting to push it and the one that's in the positive direction, because down is positive here and up is negative here, is this weight 2. Let's actually make it so it's in the numerator. Weight 2. What's opposing that force? Well, it's the force of friction. And on the bottom, what are the net mass? Well, that's just m1 plus m2, right? If we call this m1, or this is m2, and we call this m1. And that's going to be equal to our acceleration. So that's it. If we don't have the force of friction, it's an even easier problem. It's just weight 2 divided by mass 1 plus mass 2. All right. So that's it with this, the purpose of pulleys. The main purpose for pulleys is that it rotates the direction of motion, or it rotates the action of the forces. We're going to move on to forces at angles. Forces at angles use the same concepts that we learned in projectile motion, with initial vertical component of the velocity and initial horizontal component of the velocity. So we still want to draw kind of our triangle, but in this case we have it coming off of some, I don't know, space ball in this case, because this astronaut's pulling it at a force of 60 newtons, but at an angle of 30 degrees above the horizontal. And so we still need to find some, horizontal component and find some, vertical component. So to find our vertical component and our horizontal component, it's just 60 cosine of 30 degrees, where f of y would be 60 cosine of 60 sine of 30 degrees. And if we solve for this, we'll get 51.96, so about 52 newtons, and 60 sine of 30 is 30 newtons. And that's going to be helpful later when I solve for it. So we're going to use add another astronaut to the mix, and we want to find a net force. So to find the net force, here's a situation where it's very important for us to determine the components that are going in the same direction. And that's why we really like horizontal and vertical, because if I were to draw a free body diagram, I have some 60 newtons going this way at an angle of 30 degrees, and then we have 50 newtons going this way at an angle of 30 degrees. And those two are acting in different directions. They're acting in not perpendicular to each other, and it's kind of hard for us to determine a net force unless we find forces acting in a similar direction, such as in the horizontal direction or in the vertical direction. So we need to break this up into two force values and find the horizontal for each and the vertical for each, and then add those together. So let's call this 60F1 and let's call this 50F2. And so we need to find our x values and our y values. So our x values, well, we have f1 of x. Well, we already solved for that up here because 60 cosine of 30 is 52 newtons. And then we need to find our f2 of x, which is 50 cosine of 30. It's still the same in this case because the angle is to the horizontal. So we use cosine to solve for the adjacent side. So that gives me f2 of x equals 50 cosine of 30 is 43.3. I'll just round up to make this easier. And so we already know the vertical component of force 1. We solved it above, and that's 30 newtons, and it's half, so that means that the force 2 in the y direction, we would go 50 sine of 30, and that should give us 25 newtons because it's, right, sine 30 gives us half. And then we want to add these up. There's kind of another important note we have to identify, and that is the direction in which these are going. So before I just, if I just trust the cosine of 30 and sine of 30, then we might make some mistakes because I know that if I take this and let's make this and make it a little bigger, that means that my horizontal value for my F1 is going to the right. My horizontal value for, let's do this. My horizontal value for my F2 also going to the right, slightly smaller. But my vertical values are going in opposite direction. And so I need to identify which direction is positive and which direction is negative. And where this is where we can say, well, let's just make down negative just because we like making down negative. So actually this F2 of y, because it's going down, it's this 25 newtons right here. We need to make that negative, or we just need to identify that we need to subtract it from F1 of y. So my net force in the x direction is going to be the sum of these two lines, which would give me 52 plus 43. So my net force in the x direction is 95 newtons. But my net force in my y direction, we need to identify that one's going up and one's going down. So I have 30 going up, 25 going down. So I have 30 minus 25, which is equal to 5 newtons. So if I were to draw a final vector on this ball, a resultant vector on this ball, I would get a long 95 newtons to the right, and I would get a very small upward of 5 newtons. Let's take this 95 value. Let's move down here. And then my resultant vector would be this vector right there. So the net force, and let's just calculate the magnitude of the net force. We don't need the angle. That's just Pythagorean theorem. 5 squared plus 95 squared equals like this net force squared. Net force is equal to square root of 5 squared plus 95 squared, which is somewhere around 95. Of course it is. 95.1 if we're going to now include decimals. But that's how we focus. We need to find the components that are in the same direction. That's why we like horizontal and vertical. And then we add the horizontal values up and the vertical values up. So now I've got a slightly harder problem. We have two 50 Newton forces, one going up left to the and one going down left. They're both 45 degrees from the horizontal. The good news is that means we only need to solve cosine and sine once because they're equal for both 50 Newton values. And then we have one that's completely going horizontal. So let's give them names. Let's call this like equals F1. Let's call this F2. And we don't know what this is, but this is F3. So we want to find the hidden force F3. But first, we need to draw a free body diagram. So I have this ball. I have a 50 Newton force right here. There's a 50 Newton force right here. We're given the angles, so we might want to draw, like zoom in. This is 45 degrees. This is 45 degrees. And then we have one force going all the way this way. And we don't know what this value is. There's a few tricks we can do. We know that F1 of y is going to be equal and opposite to F2 of y because they are the same vector magnitude and the same angle from the horizontal, just going up and down. So we know that if I were to draw this vector and this vector, they'd be equal and they're going to cancel out. So we know from this that therefore the net force in the y direction is going to be 0 newtons. So we don't need to worry about the vertical direction. So we just need to worry about this horizontal value, and then those two should add up to this final vector on the right side. So let's do, we need f, well, we know f1 of x is going to be equal to f2 of x because they are technically the same horizontal vector. And so that's going to be equal to 50 cosine of 45. 50 cosine 45 gives me 35.4 newtons. Oh, I'm already skipping to this side, aren't I? Woo! There we go. So my F3 is only a horizontal vector value, and it's equal and opposite to 2 times one of these vectors because there's 2 of them. So I know that my F of 3 is going to be 2 times 35.4, and that's going to be 70.8 newtons. And that's how I find this final vector value. All right, that's it. So we're just now combining concepts that we've learned to help us understand more complex situations. I hope this helps.